Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, so today what I want to do is I want to kind of do two things. I want to start a review on a buck regulator that I picked up on Amazon, and I also want to show you some waveforms on it to kind of help, show how in real life how a buck is working, okay? I've done a few videos on buck regulators, and this one is going to be, looking at actual signals. Alright? Let's go look at the data sheet first, okay? Alright, so here's the Amazon page, and we're looking at the converter right here. There's the board. Now, it looks like it's $11, but you get 5% off of that. So, closer to $10.50 though. But pretty inexpensive, I think. The DC input range is 6.5 to 60, outputs 1.25 to 30. And the max current you can get is 10 amps. Now you won't be able to get 10 amps at 30 volts out. So I think the max power might be closer to 75 watts. Not sure. We'll take a look at that. But for right now, look at the dimensions. 1.18 inch, 0.79 inch by 0.39. So it is a pretty small board. Now let's look down here at the input. You see the capacitors at the input connector capacitors. Now you see a trim pot with the IC. That's a control chip with all those little support components around it, resistors, capacitors. So let's ignore that stuff for now and just look at the power. The input volt capacitors, the trace up here on the left comes up and then goes to this top transistor. That's the main bucking transistor. Okay, then down here on the bottom there's another FET and Schottky diode in parallel. So they're just doing pretty much the same thing, slightly different, but pretty much the same thing. The FET is actually controlled by the control chip, of course, and the diode is just there freewheeling. It's doing what it's supposed to do. So the connections between these two transistors and this diode is a switching node, and that's connected to the inductor. Okay, the input in the inductor. Now just above that, this top switch, the top FET, you see the two kind of beige or brown capacitors there, ceramic capacitors. They're right there at the input, okay? And that's for high frequency filtering as the transistor switching on and off. Okay, then the current goes through the inductor out the other side, and then there's a sense resistor right there, 10 milliohms, and that's current sense. So then from the current sense it goes into the output capacitors and the output. Okay, now here let's just look at the schematic. This, you can see, if you're familiar with that symbol, is LT, Linear Technology, which is owned by Analog Devices now. Okay, let's go look at their data sheet. Okay, let's look at the data sheet. It's right here, the LT3800. And I'm just going to go over this stuff really quick just so you can take a look at that if you want. But we're going to go over this in more detail in the next video when we talk about control chips. But for now, let's just look at this, the schematic. And actually, just look over to your right for now, the efficiency versus power loss. Up on the left part of the scale is efficiency. You see 95% is right across the top grid. And you see a couple of the curves right above 95%. And that's 24 volts. The next one down is 36, then 48, and then 60. So it's less efficient the higher voltage you go. That, some people might wonder why that is. And if in this example, they have 12 volts at the output. So if you have a lot of volts that you're stepping down, you're switching through a lot of voltage, which is more losses. Okay, if you don't have to switch down that much, and also if you think about 24 volts in, that's kind of like our examples have been. At 50% duty cycle, you get half that voltage, 12 volts out. So that means the diode and the transistor both get a share half the current. And so it's a little bit more efficient at 24 volts, so just above 95%. And also, you notice the peak is right around 1 or 2 amps. So right around 2 amps is where you're going to get the best efficiency in this case. So 12 volts out, 2 amps, that's 24 watts, and 24 volts in, that's your most efficient. Now this bottom curve, in case you're looking at it, the one that kind of starts off bottom goes up, that's just power loss. That's the grid over here to the right. It's showing the actual efficiency loss. So it's, and this is with the 48 volts in. So this is not quite the worst case, but almost worst case. So at 2 amps, you're losing about 1.5 watts. Right here at 3 amps, you're losing just over 2 watts. So that's with 48 volts in. That's what that's showing. It's just basically showing you the other end of what happens with the efficiency. Okay, so backward to the schematic. At the top left corner, you see VN. You have 2 bulk capacitors shown right there on the schematic. Then come across the top. Let's ignore the control chip and all that stuff. You just come across to the power connection, and then you come over and you see 3 1 microfarad caps. We only saw, I think, 2, right? One must have been on the other side of the board. Well, this is also an example app note. This isn't the exact circuit we have on our board. But it's neat that they show these ceramic capacitors right next to the transistor, because that's where you actually want them on the board. So that's another thing that's nice on schematics, when you kind of represent what you want physically on the board in your schematic. So up here's your switching FET, your main FET. That's where the current first hits. Then it comes out into the switching node. Now you see the synchronous FET down here at the bottom and parallel with the Schottky rectifier. So this is your switching node between all these connections and your inductor. So that's the switching node, because this node here gets pulled up really high when that transistor is on, and then when it's off, it gets pulled essentially down to ground, just below ground, a diode drop below, or a transistor drop below, whichever way you look at it with in this case. So this guy is switching, very high, very low. Okay, switching the full range of the input voltage. So that's why it's a switching node. This is where EMI can radiate from, and this is in your layout, you want small. So if we go back to the board and look at this right here in the middle, where the 2 transistors connect together with the Schottky diode and the inductor, that's kept pretty darn tight. And again, there's only 2 ceramic capacitors here, but in this case, I'm sure they thought that was good enough, and it's, again, not exactly, the input voltage and output voltage specs are a little bit different on this board than that example circuit in LT. So, but anyway, yeah, there we go. Pretty interesting, right? Now this is a 10 milliohm resistor. I'm just curious, didn't really pay attention. Over here, they have a 15 milliohm. So see, now as the current goes through the inductor, it comes out and goes through a sense resistor before it goes to those ceramic caps right here on the left, and then the bulk capacitors on the right. And that sense resistor, in this case 15 ohms, milliohms, and that would go back to this plus and minus sense on this control chip. So anyway, that's just monitoring the current for your current protection, okay? Okay guys, I have that board here on the bench and ready to start doing the testing, but I want to show you my little whiteboard here first. I've shown you this circuit in the last couple videos, and I just want to talk about this a little bit more, okay? This is showing the main part of the buck converter. We have our transistor that's bucking the input voltage from the output, and basically the duty cycle I've talked about, the time it's on versus the time it's off,
is providing the average voltage for the output. So in this case, we're going to use 30 volts at the input and have 20 volts. So, you know, in this case, we'd have about 2/3 of the time on, 1/3 of the time off, and puts about 2/3 voltage out here, right? Well, now the function of the diode, we've talked about that. When the transistor turns off, then the diode conducts current, allows the inductor to keep on conducting. So when the transistor's on, lets current ramp up in the inductor, and then when it turns off, the diode lets it ramp back down. And if they're like this, one ramps up, one ramps down, and then a cycle starts again, then that's great. That's called continuous mode conduction. The inductor always has current. And so it's continuous versus discontinuous, like in this case, where it ramps down, it waits a while before it ramps back up, and then it, you know, so there's some dead time in between. That's when the inductor, I call it running dry. That's when it's out of current, it's out of juice. So it's not conducting, it's discontinuous. Now in this picture, it looks like this one, okay? So now I want to show you this. Now this is the switching node, okay? I want to show you what the switching node looks like. That's the voltage. So this is the current waveforms. In this case, where there's some dead time between, you know, the inductor ran out of current, the output just didn't need that much current. So the inductor only charged so much and then discharged so much. So there's some dead time between, so it's discontinuous. The voltage, as the thing's charging, okay, so he starts off running high, and he's at 30 volts because the transistor's on, so he's got 30 volts here. Well then, when he turns off, then the voltage here gets, this node gets pulled down to ground, basically, by the diode. There's a diode drop there, and so we're down here at 0, essentially, close. And then what happens is the inductor runs out of current. Well then the voltage here, there's no current flowing, so the voltage just floats up to the output voltage. What's over here, this open circuit here, so basically it floats to this, but it rings a little bit first. You know, there's a capacitor in here, there's some inductance, and it just sits there and rings a little bit. And then he settles down to essentially what the output voltage is. Then, because since the diode's not conducting anymore, it's almost like an open circuit, right? And so we got the output voltage right here, and then what happens, the transistor turns back on, so it pulls it back up to 30 volts, and then you get this. So you get that kind of looking waveform, and then it repeats again, and there's this, you know, kind of funky looking waveform. That's discontinuous. So you get one thing, besides some other issues, you get a little ringing there, so that could be an EMI problem. That's on your switching node. Alright, so in a case where it's like this, where it just barely starts running out of current when it charges up again, well then it looks like this. This transistor's on, put 30 volts right here, the guy charges up, turns off, he starts to discharge, so the diode's holding it to essentially 0 volts, and then he turns back on again, so he pulls it back up to 30 volts. He pulls this node back up to 30 volts, so he's just going get pulled down by the diode and then up by the transistor, which turns off the diode. So that's what a continuous mode and discontinuous. We're going to come looking on the scope now, okay? And something else I want to show you is this voltage here. Remember what I was talking about before, it's really a diode drop there, because this is ground and this is 0.7 volts below ground. So it's actually, you know, negative 0.7 volts through here. So let's come over here and take a look. Alright, so I'm just going to show you the board here. You can see the board, the inductor. I pushed it over on its side and I added this wire. So it's, I'm going to have to solder it a little bit better there. So it's going to, here's a pin of the inductor, and so I soldered one end to the pin and the other end where the inductor went. So just added maybe a little bit of inductance to this, no big deal, but we're going to use this current probe to clamp on there and watch the current. Meanwhile, I put a wire down here on on the input side of the inductor, which is a switching node, and I put that wire right down on there. There's this little square right here is the switching node. Here's the other pin of the inductor where it come out. That's the output. But this is a switching node. So we've got some differential probes. I was kind of looking at using two different scopes. I got the MixSig and I've got the Pico on my computer using the Apple with the new software. I'm just kind of comparing the differential probes on the two different scopes right now. I'm going to do a video on that. But yeah, so there's our circuit. We're going to use this load right here to demonstrate how this board's going to work, okay? On essentially how buck regulators work. Let's do it.
Okay guys, we're up and running. I've got channel A up here in the blue. You see the 0 setting here, reference setting. It's on the left scale. Channel 4 is this yellow one, and the reference is right here, 0, and it's on the right side of the screen right here, down here, 0. Okay, so I've got them separated so you can see as right here, this waveform you see over here on the right side of the screen is 30 volts. So when it's up to 30 volts right here, we see the current charging in the inductor. It's ramping up, and then it peaks out right here, right where the transistor turns off, and then the diode pulls it down to close to 0, and we see a discharge. Okay, and then after that it just kind of rings. The voltage just pops up because the diode's not really conducting anymore. It just kind of rings, and it's set right here at the output, which is 20 volts. So you can see it just finally settles at 20 volts, and then we get another cycle, turns back on. Now down here at the bottom left corner you see 200 kilohertz. So we're running at 200 kilohertz. Right here above that you see the RMS current that we're reading on that wave, and the min-max. You see the statistics here. Over here in the middle is the peak-to-peak value. Okay, you can see the scale here. It's 0, and it goes up to about 0.6 probably right there. So it's ramping up at 0.6, come down. Okay, and then we have some dead time here. Okay, now over here on the right, down here at the bottom of the screen, I have duty cycle. Now this is 78%. This is, I think what it's doing is it's actually counting from here, even though it's just ringing. I think it's counting from here all the way over. So that's not quite accurate. That's just what the scope sees. It thinks it's turning off here, so it's counting this as one, portion of the cycle. So what I want you to do is, see, I'm triggering right here in the middle of the screen. See that? So what I want you to do is look from here to the left. It's almost a grid, not quite a grid. That's the actual time the transistor's on when it's putting out 30 volts here at the switching node. Okay, so again, if I didn't mention that, this is a switching node. So this is going up and down. When the transistor turns on, goes 30 volts, then gets pulled down to the diode. So this is a switching node, and this is the ringing that I'm talking about when there's just not enough current to keep the inductor charged all the time. So let's go ahead and ramp up the current. Okay, so let me pull the 0 line down here. Okay, I'll pull the 0 right down to here so we can get it in the screen a little bit higher. But look how full this is now. This is that critical conduction I talked about in the last video, where we just barely come down to 0 and then we turn back on. Okay, if I take this up just slightly higher, oops, I'll just take it just barely above it. See right there, it's just coming above. I don't want to hit the overcurrent trip, but okay, I'll drop it down. Okay, now, but this duty cycle is set by the 20 volts on the output and the 30 volts at the input. So this is what it looks like. So basically our trigger point's right here, and see, we're on for 1 and about 3/4 of a cycle, and we're off for probably less than a cycle. So it's about 2/3 to 1/3 of the time. Okay, now what I want to do is I'm going to bring up the input voltage, and you'll see that this gets, the off time gets narrower. This is starting to get narrower because, see, the voltage is going up and it's getting narrower because it doesn't have to put as much voltage out to maintain that 20. I'm at 40 volts right now, so now it's about 50% duty cycle. See right down here, 50% duty cycle. Now I'll drop it down close to 20, so it's just barely bucking. And see, now it's on for a long time because we're just set just above the voltage. You can see right over here, 25 volts, and it's trying to maintain 20 volts, so it's on almost the full time, so it's off just portion. So that's duty cycle control. You can see how the current is above 0 now because it's ramping up, and then look how fast it ramps down because the difference in voltages, so it changes the ramp because of the voltage across the inductor. And as we get 50%, as I go up to 50%, you'll see the ramp on both up and down is the same because it's 50% duty cycle. Okay.
All right, so let me know what you think about that. Did that, being able to visualize that and see it actually on the screen, in the scope shot, did that help make you understand that a little bit better? I'm just trying to really drive into this buck converter because it's going to help with the other converters a lot when you really fully understand the buck converter. Okay. Oh, I want to thank my patrons. Thanks a lot, guys. Appreciate you guys. And you can become a patron for those $1 a month. Links are all below, and the links for the previous videos are below too. Or I think I'll have the link to the playlist below. Okay, so you can watch the buck converter from the start or jump around if you want. But all right, guys, hope you like that. And the next video, we're going to start talking. We're going to actually design the inductor, and we're going to design the capacitors too. Okay, we're going to look at the trade-offs on those capacitors and the inductor. Then after that, we'll come back to this buck converter, and we're going to, we'll use this buck converter as an example too. We'll see how they designed it, and that way we can actually look at this buck converter board and see what it looks like. Okay? All right. Hey, thanks for watching. See you next time.